process. Okay, so next one is Vmos. It is vertical metal oxide silicon MOSFET. So it is vertical metal oxide silicon MOSFET. It is also a power MOSFET, and the fabrication diagram you can see, you have a, the gate structure is having a V. Okay, you can see a V type structure in the gate. So here in the DMOS, you can see the gate structure is flat, and below the gate you have the insulating layer. But here you see the gate structure is of a V type. Other things are going to be exactly same. See, no other change in the structure. You have an N plus and P below the source on both sides, and between the drain is having an N plus region, and between the source and drain you have the N type drifting region. So the structure represents a symbol V. Okay, the terminals of the device are connected to the metallic surface. You take out metallic wire from these layer source and your gate, and here you take from your drain. So silicon dioxide is placed between the gate and the P type. Yes, so below the gate region, you have the layer of SiO2, which is going to act like an insulating region. Okay, the drain and the source, and between the drain and the source for induced N channel. So between the drain and the source, you have an N channel. So which means that it is going to be the enhancement mode of operation. If you have a P channel, it's going to be the depletion mode, and if you have N channel, it's going to be the enhancement mode of operation of your Vmos. So the term vertical is because the channel is formed in the vertical direction rather than the horizontal direction of the device. Moreover, the channel has shape of the V. So below the gate, you have channel formation in the shape of the V. Since the gate is in the form of a V, channel formation is also in the form of a V, which is an important characteristics of the device. So the source, the electrons from the majority carriers from the source will drift here, and they will reach here like this. So they will reach the drain in this way, and the majority carriers from this side of the source will drift through this channel, and it will reach the drain in the vertical direction. So the construction of Vmos is very simple, leaving out some transition levels of doping. Except this V layer, the other layers are very, very simple to fabricate because it follows the same structure of your DMOS. Only thing, the gate is in the shape of the V. The channel is induced or enhanced the narrow P-type region of the device if the positive voltage is applied to the drain, negative voltage to the source, or same positive voltage is applied to the gate. So if you apply positive voltage to the gate, equal and opposite charge is diffused. So N region, you will have a lot of negative. So it is going to increase the number of electrons. So it is going to be acting in the enhancement mode. But at the same time, if you are going to apply negative supply to the source, it will induce positive region into the N-type region. So it will decrease the number of electrons in the N-type region. So it is going to maybe acting in the depletion mode. So the same device can be made to work in both depletion mode and enhancement mode just by reversing the gate supply, DC supply which you give to your gate. So the vertical height of your P region will define the length of the channel. So the vertical height of P region is going to define the length of channel, and it is going to be in the order of micrometers, 1 to 2 micrometers only. So diffusion layer such as the diffusion region is in the order of 2 microns, right? So it is going to be in the fraction of micrometers only. With precise fabricating mechanism, you can ensure that the length is 1 to 2 micrometers, and the diffusion layers can be in the range of fractions of micrometers. So that can be ensured by proper fabricating mechanisms. And the resistant levels of the the power dissipation of the device will be reduced because of the reduced channel length. The channel length is in the form of V, right? So it is reduced, right? So all the other parameters will also be reducing. So the contact area can be increased in the vertical mode, which contributes the further reduction in resistance level, and which will ensure that more current flow is going to happen. Since we are growing the device in a vertical mode, so if you are growing the device in a vertical mode, you are increasing the area, you are reducing the channel length. So with that, the resistance is reduced, the area is increased, so the more current will be able to flow through the device. So two conduction paths exist between the drain and the source. So we have two conduction path existing as I shown the diagram. So this is one path from the left side of the source and this is one path from the right side of the source. So you have two conduction paths existing for the current to flow between the source and the drain. Okay, so this conduction path, because of the current is additive, so it will result in a very high current rating. So what is the final effect? The you can have amperes of current flowing through the device, and the power level is also going to be more. Okay, so because of this arrangement, you have the currents to be additive. So two currents will be flowing from the source to drain, resulting in a very high current flow and the higher power generation in the device. So V MOSFETs have reduced channel resistance and high current rating compared to the conventional MOSFETs. The conventional power MOSFETs will have this drawback, but V MOSFETs are operating in a very high power level because the channel resistance is very, very less. Since the power handling, current handling, and power handling capability is very high in VMOS, VMOS transistors are used in power amplifier applications where the high power requirement is always there. Another one important characteristic is vertical construction. So vertical construction overcomes the temperature, which overcomes the thermal runaway. So it reduces the going to increase, the resistance is also going to increase and the current will be reduced. So which will ensure that the device will be safe always. So when the temperature of the device is going to increase, the current resistance will also increase because I have said the device is going to have a positive temperature coefficient, right? So positive temperature coefficient means any increase in temperature, all the parameters will increase. So the resistance will increase. When the resistance is going to increase, the current is going to reduce. When the current is going to reduce, the safer operation of the device is ensured. So this causes the reduction in drain current. For the conventional devices, the drain current will increase. But actually, in conventional devices, the drain current will also increase. But here, because of this positive temperature coefficient, even though the temperature is increasing, here we don't have the increase in drain current. So the device is going to have a safer operating region. So when the device is going to have negative temperature coefficient, then the drain current will increase, which will in turn affect the temperature stability and thermal runaway. So, but this device is going to have a positive temperature coefficient, right? So we are very safe here because we need not worry about the temperature stability and thermal runaway of the device. And also this VMOS will have a faster switching time when compared to the conventional planar structure of your MOSFET. Okay, the switching time is less than one half of that encountered in BJT. So switching time half of the BJT. If the BJT is taking 2 nanoseconds for switching from on state to off state, your VMOS device will take only 1 nanosecond. It is very fast. The switching time is exactly reduced by half. Okay, it is less than half. So maximum value is reduced by half, and it will be even more less by choosing this vertical structure of construction. Okay, by choosing the vertical planar, conventional planar devices are very, very slow. By choosing this vertical layer of construction and having a V-type channel below the gate, we are ensuring the faster operation of the MOSFET. Okay, and the advantage is going to be the switching time is very, very less. It is almost less than one half of what is available in conventional BJT. So this makes VMOS an attractive option for using it as a high voltage and high frequency device. High voltage and high frequency device.